Okay, well, last time we got into the amine formations. Okay, so today what we want to do is look at the amine mechanism. Okay, how do we form these things? Okay. So let's take a molecule like this here. Remember what we did? We took an aldehyde or a ketone and react with an amine. And we also used H+ with an acid catalyst. Okay? So this was the setup. Let's take this through the mechanism to see how amines formed, and you'll see this will follow the exact mechanism that we've been doing for the other ones. Okay? So what do you think the first step here will be? The oxygen attacks the proton. Okay? So let's add that on. Okay? So again, for the purpose of that, it makes the oxygen more electronegative, so it makes that carbonyl carbon more electropositive, more reactive for the nucleophile, which in this case will be the amine. So that's what we'll bring in the next step. Question on that? Okay, so now the nitrogen will attack where? The carbonyl carbon. And kick those pi electrons up to the oxygen. So now the amine has added on. We got a positive charge on nitrogen, so that will make these two hydrogens here acidic. So we can choose either hydrogen to deprotonate, so let's bring in another amine, and it can attack either hydrogen so let's take that one, then these electrons dump into the nitrogen. So we get this molecule here. Okay. So this molecule here, we're kind of at the halfway point. Remember, if we were adding on an alcohol, this would have been a hemiacetal or a hemiketal. Okay? So we're halfway here. One other note, just by way of reminder, note that the amine is used here and here, but it's attacking different things. when it attacks a hydrogen, this is acting as a base. When it's attacking a carbon, it's acting as a nucleophile. Okay? So remember, that's the difference between a lone pair in terms of what it attacks. Okay, so let's go on to the next step. So we're going to bring in another proton. And what's going to attack the H+? The oxygen or the nitrogen? Oxygen. If we do the nitrogen, we go backwards. Okay? So we don't want to go backwards. We want to go forward. So let's have an attack here. So if that attacks there, what molecule do we create? Water, which is a good leaving group. So let's get rid of our leaving group. So water leaves, and we get this carbocation forming. What's special about this carbocation? We can draw what? A resonance structure. Okay? So it's the exact same mechanism that we did last time. Okay, so let's draw resonance for that. Get this structure here. Let me put brackets here so we can see the two resonance structures. Okay. Remember last time we used this resonance structure to go on to our last step. This time we're going to use this resonance structure here. Why is that? Remember the amine is what? Carbon double bonded to nitrogen. So we're almost there. What do we have to do? Remove that acidic hydrogen. Okay? So this is acidic, the same reason these were acidic. Okay? Positive on nitrogen. Positive on nitrogen. So let's just bring in the base one more time. Bring in our amine, and act as the base. So it takes it, and it's going to take these electrons to dump on the nitrogen. And so we get our amine. Do you remember what kind of amine that was called? Ship base. So this is our next very important mechanism that we need to know. Okay? And it's exactly the same thing like the water and the alcohols. Okay. So let's go back over it again, make sure we understand it. Again, see how you answered the questions? You didn't have to memorize the whole thing, but you just let each step feed itself in terms of what to do. Okay? So first step, protonation to make the carbonyl more reactive. Then the nucleophile adds on to create acidic hydrogens. I remove an acidic hydrogen with base. I'm halfway there. I next choose the oxygen, so I go forwards to give me water, which is a good leaving group. So it leaves. Give me the carbocation here, which is resonance stabilized. So the only thing new is that we use this resonance structure, and so remove that acidic hydrogen there. Okay. Any questions on that mechanism? Okay, so you have a couple that you should have under your belt so far. Okay, so this thing here follows all the nucleophiles that we've been covering. Okay? So remember the nucleophiles. We've done water. We've done alcohols. We did HCN, KCN to make cyanohydrins. We did the Grignard reagent, okay, where that attacked the carbonyl. Okay, and lastly, what we've done are the amines. Okay, so all these 5 reactions follow the same mechanism. Okay, except these 2 and this one here, they are a little bit more extended. Okay. So make sure you can do each of these mechanisms. Has anybody taken the quiz yet on Monday? Okay.
Yeah.
So you saw I asked for the mechanism of water. Okay. So that was just to get you started. Okay. So make sure you can do each of these for the next exam. I might not ask all of them, but you don't know which one I'll ask. So you need to be ready for any of them. Okay, so if you look at your outline, that makes us done with all the way down to 11 and 12. Okay. So that brings us to number 13, something called the silver mirror test. Silver mirror test. Here what we're going to do is take some kind of aldehyde, okay, whatever it is, and we're going to react it with these reagents. amine silver and some base. Okay. And these reagents make up what's called the, okay, turn the phone off. What's called the Tollens reagent. Okay. And here's what forms in this reaction. Okay, the aldehyde turns into this group. Some silver there. And then we get ammonia. Okay. So when you react an aldehyde with a Tollens reagent, you get these products. The main product we're going to focus on is this thing here. I heard somebody say, what's the down arrow mean? What does the down arrow mean? You learned that back in general chemistry. Means it precipitates. Okay, so what you start seeing is silver precipitating out of solution. Okay. And what happens is it coats the flask with silver, and so it creates a shiny mirror, and so we call it the silver mirror test. Okay. And this only works for aldehydes. It doesn't work for any other kind of carbonyl compound. Okay? So for example, if you had this molecule here, cyclohexanone, is that an aldehyde? No, it's a ketone. So if I reacted it with the Tollens reagent, what do you think would happen? Nothing. Get no reaction. Okay? So the big thing you want to see would be any silver floating out of the solution. Okay? But if you took something like, oh, I don't know, an aldehyde like benzaldehyde, and reacted it with the Tollens reagent, then you would see your silver coming right out. That'd be the main thing you look for. Okay? So what this test is, it's like litmus paper. What do you use litmus paper for? To see if something's an acid or a base. Okay? So if you wanted to see if something was an acid, you would use blue litmus paper and see if it turned pink. If it did, it was acidic. Same thing here. If I had a bunch of unknown jars and I wanted to see if something was an aldehyde, okay, just throw in some Tollens reagent, look for silver coming out, and it's done. I know it is. If I don't see any silver come out, then I know it wasn't an aldehyde. That's all I can say. Any questions on the silver mirror test?
So for the silver mirror test, would those be reactions or just a question to know that?
Right. So know what product forms and how to use it. Okay, so if you look on your outline sheet, you'll see number 14, 15, and 16. You might want to put brackets around those to show that these all go together. Okay, these will be very similar reactions. Okay, so what we're going to look at in these reactions, they'll undergo the same heading. And that heading is the reduction of a carbonyl. The reduction of a carbonyl. Okay? So remember that a carbonyl is this functional group. Okay? So if I wanted to reduce it, what do you think is going to happen to it? Okay? What's going to reduce? The double bond, what's that going to go to? A single bond. Okay? But I need something on the oxygen now. Okay? So we're going to reduce the carbonyl to an alcohol. Okay? And we're going to look at some reagents to be able to do that. Okay? So let's look at the first reagent. Okay. The first reagent is this thing here, NaBH4. Then we mix in some alcohol like methanol or ethanol. Okay. NaBH4, this is what's called sodium borohydride. Okay. Have you used that in the lab?
Yes.
Yeah. Oh, so you did an experiment?
Mhm.
When did you do that?
Last time.
Okay. So you're familiar with it. All right, good. All right. So what's the main property of sodium borohydride? Well, you draw out its Lewis structure. You get this here. So 4 hydrogens on the boron, and the boron gets a negative charge. Okay. Well, what this acts as, boron would like to go back to neutral, and so it would like to give off that hydrogen with a lone pair. In hydrogen with a lone pair is what's called the hydride ion. Okay? Okay, so we have H, which is hydrogen. We have H plus, which is a proton. And now we have H minus, which is the hydride ion. What can the hydride ion act as? What can it act as? George, what can it act as? Oh, I'm sorry? Okay, it can act as a what, a nucleophile or a base. Okay, why is that? Lone pair. Okay, back in chapter 2. Okay, so it's this thing here that we're going to focus on. It's going to act as a nucleophile. Okay? So anytime you see sodium borohydride, okay, you don't have to worry about all the atoms. Just tell yourself that it's going to act as H minus. So let's take this knowledge and let's do a reaction with sodium borohydride. Okay, so let's suppose we wanted to look at acetone. Okay, and we reacted it with sodium borohydride and an alcohol like methanol. Okay, so we've already said that sodium borohydride will act as H minus. Okay. So, if it does that, the only thing it can attack over here is the electrophilic carbon, and then move these pi electrons up there. Okay. So here's the mechanism. Let's draw the result. So here the hydrogen is added on. And now we have O minus there. Okay. What do you think that O minus wants to do? Okay. It's a base, so it likes to maybe grab an acidic hydrogen. So that's where the alcohol comes into play. Okay, so the oxygen goes ahead and takes the hydrogen. And we get our alcohol. Okay. Any questions on that? Okay, so that's how these two hydrogens have added across the carbonyl to reduce the carbonyl to an alcohol. Okay? If you remember way back to the beginning of this chapter, what were we doing? We were going from the alcohol to the carbonyl. How did we go from here to here? What reagent? PCC. Okay, so some of you have been studying. PCC oxidizes, sodium borohydride reduces. Okay, so you can go either direction depending what your reagent is. Okay, any questions on sodium borohydride? Okay, let's look at another one. Our second reagent is this one here, LiAlH4, which stands for lithium aluminum hydride. oftentimes we can abbreviate this as LAH. If you look at the name, how is this similar to the last one we used? The hydride part, right? Hydride. So, this thing is going to act the same way sodium borohydride did, give off a hydride ion. Okay? So you can remember that from the name. So it's going to act as H minus 2. So it's going to do what? The exact same reaction. Okay? So let's maybe use a different carbonyl here. So it'll convert the carbonyl to the alcohol. Okay. Questions on that? You might say, well, that doesn't make any difference. What's the difference in the reagents? Okay, they both do the same thing. Well, that's exactly right. Okay, lithium aluminum hydride is a little bit stronger, so it's a much more aggressive reagent. Okay, and so it does the conversion a lot faster. Sodium borohydride is a little bit more sluggish. Okay, it's a little bit more lazy. Okay, so it takes a little bit longer. Okay, so this is a real more efficient one, but as a result, it's a more expensive reagent. So that's why we give you sodium borohydride in the lab. It's less expensive. Okay.
I have a question. So is it safe to say, like, if you have two carbonyl groups on that like group structure, that the
That's right.
LIOH would be
It'll convert both.
But that individual.
It'll convert them too.
Oh,
Okay. So, yeah, she was asking if you had another carbonyl on here, would it convert both of them? The answer is yes. So if there was a carbonyl down here, then you'd have an OH here and an OH down there too. Any other questions? All right, let's look at one more reagent. Okay, this one here, we're going to use hydrogen gas and nickel, or you can even use platinum. Okay. Let's look by way of review. Let's suppose we had this alkene plus hydrogen. Remember this reaction back from 241? Okay. What did it do to the double bond? Okay. So there's already a hydrogen on each carbon of the double bond. But it adds two more there. So it converts the double bond to a single bond. Okay, so we call that a hydrogenation reaction. Okay, it reduced the double bond. Well, guess what? It's going to do the exact same thing to a carbonyl. Okay. took that ketone here. This will convert the carbonyl, this time to the alcohol again. Any questions on that? All right, so here were 3 ways to reduce a carbonyl to the alcohol. Okay, so make sure you remember all those reagents. You can see these reactions are piling up a little bit here. Make sure you're keeping track, like she is, on index cards. Okay, because they're going to keep piling up, especially when we get into chapter 19 with the amines. We'll be getting a lot of reactions in there too. Okay. All right, so we're going to stop here for today, and I got a survey I want you to fill out, and then we'll call it a day.